In this video, we are going to study about ideal gas equation. We know Boyle's law, that is volume is inversely proportional to pressure at constant temperature and constant number of moles. Charles' law, that is volume is directly proportional to temperature where pressure and number of moles are constant. And Avogadro's hypothesis, where volume is directly proportional to number of moles and pressure and temperature are constant. So using all the three laws, we can derive the ideal gas equation. So volume is directly proportional to number of moles, and volume is directly proportional to temperature, and volume is inversely proportional to pressure. So combining all the three laws, we will get an equation, that is volume is directly proportional to NT by P. So if we remove this proportionality symbol, we can introduce a constant. Now here I am introducing an universal gas constant, that is R. So PV is equal to nRT. As P comes to the opposite side of the equation, it will multiply with V. So PV is equal to nRT. Here P is pressure, V is volume, N is equal to number of moles, T is temperature, and R is universal gas constant. And R will have different values at different conditions. Okay. At 1 atmospheric pressure and volume 22.414 decimeter cube and mole 1 mole and temperature 273.15 Kelvin, the value of R will be 0.0821 decimeter cube, atmosphere, mole inverse and Kelvin inverse. This value is more important and this value is most commonly used value.
Start.
Now the another value for R. Under standard conditions, that is under standard temperature and pressure, and STP values for pressure is 1 bar, that is 10 power 5 pascals, and volume is 22.71 into 10 to the power of minus 3 meter cube, number of moles is 1 and temperature is 273.15 Kelvin, that is 0 degrees Celsius. So R is equal to, we know the ideal gas equation, that is PV is equal to nRT. Rearranging the equation, R will be equal to PV by NT. Pressure is 10 power 5 pascal. Volume is 22.71 and into 10 to the power of minus 8. And number of moles is 1 and temperature is 273.15 Kelvin. So if we solve this for values, we will get an answer 8.314 Pascal, meter cube, Kelvin inverse, mole inverse. So whenever in the question they give at standard temperature and pressure, we should use this value for R, and the pressure at STP is 10 power 5 pascals, 10 to the power of 5 pascals, and temperature is 273 Kelvin. Volume will be 22.71 into 10 to the power of minus 3 meter cube. So let us discuss some questions. First question. So the given values, the given parameters are, we don't know the pressure, number of moles is 2 moles of sulfur hexafluoride and volume is 6 decimeter cube, temperature is 70 degrees Celsius. So we cannot substitute the value of temperature in terms of degrees Celsius. So we are converting this value into Kelvin. So we are adding 273 with the 70 to get the Kelvin value. That will be, let us see. So we need to find out the value of pressure. So we know the ideal gas equation is PV is equal to nRT. Rearranging the equation, P is equal to nRT by V. So P is equal to nRT by V is equal to, the R value is 0.0821 and the N value is 2. Volume, the T value is 70 plus 273. Volume is 6. Here volume is given in terms of decimeter cube. That is why we are using this value of R, this value for R. If volume is given in terms of meter cube, we have to use that another value for R, that is 8.314. That is 8.314. Okay. Now we are using this 0.0821 because the volume is given in terms of decimeter cube. And now if we solve these values, we will get an answer of 9.39 atmosphere. So this is the value of pressure. Coming to the next question, the question is, a small bubble rises from the bottom of a lake where the temperature and pressure are, temperature is 8 degrees Celsius and the pressure is 6.4 atmosphere, T1 and P1. T1 is 8 degrees Celsius, P1 is 6.4 atmosphere. To the water surface where the temperature is 25 degrees Celsius. Here T2 is 25 degrees Celsius and P2 is 1 atmosphere. Calculate the final volume. That is V2 we have to find out, and of the bubble, if its initial volume is 2.1 ml, V1 is given. So we know the value of P1, P2, T1, T2 and V1. We need to find out the value of V2. So writing the given values, T1 is equal to 8 degrees Celsius, T2 is equal to 25 degrees Celsius, P1 is 6.4 atmosphere, P2 is 1 atmosphere. Here the pressure is given in terms of atmosphere, so we are using the value of R as 0.0821. But in this equation, in this sum, we need not use the R values. So T1 is 8 degrees Celsius, T2 is 25 degrees Celsius, P1 is 6.4 atmosphere, P2 is 1 atmosphere. V1 is 2.1 ml. We have to convert it into decimeters cube. That is why I am converting this milliliter into liter. Liter is otherwise decimeter cube. So liter and decimeter both are more or less same. So we are converting this 2.1 ml into 2.1 liters. So that I am here multiplying it with 10 to the power of minus 3. So here the volume of the bubble will be same. This is a lake and this is the bottom of the lake. This is the upper surface. A small bubble is rising from bottom to surface. So air bubble. This air bubble will have some amount of gas. That number of molecules or number of moles of gas present inside the air bubble will be same at the bottom and at the surface. Both the bubble at the bottom will go to the surface. Same bubble is going from bottom to surface. So there won't be any change in the number of moles. So here N will be constant and we need to find out the value of V2. So now we need to compare the given values. So PV is equal to nRT is the ideal gas equation, and now we are comparing P1 V1 by P2 V2 is equal to N1 RT1 divided by N2 RT2. Here N1 is equal to N2 because same air bubble is moving from bottom to surface of the lake. So same number of moles will be present in the gas bubble. There is no change in the number of moles. So N is constant. We can cancel the N. Okay, we can also cancel the R values because both the R values will be same. So then the equation will be P1 V1 by P2 VT is equal to T1 by T2. P1 is 6.4 atmosphere. V1 is 2.1 ml, that is 2.1 into 10 to the power of minus 3 liter, divided by P2 is 1 atmosphere. V2 we don't know, V2 we have to find out, and then T1 is given is 8 degrees Celsius, right? Given T1 value is 8 degrees Celsius, we have to convert it into Kelvin. So 273 plus 8 will be 281 Kelvin. T2 is 25 degrees Celsius, that will be 273 plus 25 will be 298 Kelvin. Okay, T1 here T1 is 281 Kelvin and T2 is 298 Kelvin. So rearranging the equation, V2 will come here and this 281 will go to the denominator, 298 will go to the numerator. So if we solve we will get an answer of 14.24 into 10 to the power of minus 3 liter. So this is the volume of air bubble when it comes to the surface of the lake, because at the surface there is different pressure and atmosphere, and at the bottom there is some different pressure and temperature. The temperature at bottom and the temperature at the surface is not same. At the same time, the pressure at the bottom and the pressure at the surface of the lake is also not same. So due to the change in pressure and temperature from bottom to surface, the volume will also change. So this is the second question. The question is 35 ml of dry hydrogen gas were collected at 6 degrees Celsius and 758 millimeter Hg pressure. So this is the millimeter Hg pressure and this is the pressure, volume, temperature. What is the volume in ml of hydrogen at STP? STP means the temperature will be 273 Kelvin and the pressure will be 10 power 5 pascals. Okay, pressure will be 10 power 5 pascals and temperature will be 273 Kelvin, and we need to find out the value of volume. So T2 is 273, P2 is 10 power 5, V2 we have to find out, V1 is 35, T1 is 6 degrees Celsius and P1 is 758 millimeter mercury. So we have to convert this into, we should not substitute the value of temperature in terms of Celsius. We have to convert it into SI unit. So I am converting the 6 degrees Celsius into Kelvin. Just simply I am adding 273 with the given value. 6 plus 273 will be 279. And I am converting this pressure value in terms of millimeter mercury into pascals. So 1 millimeter mercury is equal to 133 pascals. Then 758 millimeter mercury will be equal to how many pascals? 133 into 758. Here 133 pascals. We need to convert the pressure value from millimeter mercury to pascals. So 1 millimeter mercury is equal to 133 pascals. Then 758 millimeter mercury will be equal to 758 into 133 pascals. And volume, we have to convert this value in terms of milliliter to liter or decimeter cube. Both are same. So we need to convert. So we know that 1000 ml is equal to 1 liter. Then 35 ml will be equal to 35 into 10 to the power of minus 3 liter. I am converting this value of volume from ml into decimeter cube. Now I am going to substitute the values. T2, we know that at STP temperature will be 273 Kelvin and Pascal will be 10 power 5 pascals. That is pressure will be 10 power 5 pascals. And V2 we have to find out. We know the formula P1 V1 by T1 is equal to P2 V2 by T2. I derive this from the ideal gas equations. So ideal gas equation is PV is equal to nRT, which is ideal gas equation. P1, so comparing this one, P1, comparing this ideal gas equation, P1 V1 by P2 V2 is equal to N1 R T1 divided by N2 R T2. Okay, so we know the values of, here we have to cancel this R because both the R's are having same value, and the number of moles here is also same. Because same gas only, different temperature, pressure and volumes, but same gas, same number of moles. So N1 and N2 will get cancelled. So then it will be P1 V1 by P2 V2 is equal to T1 by T2. Okay. So keeping this V2 here, P2 will come to the denominator and T2 will go to the numerator. P1 is 758 millimeter mercury. We have to convert it into pascals. So I am multiplying it with 133. So 758 into 133, that is pressure. Volume is V1, volume is 35 ml, that is converting into 35 into 10 to the power of minus 3 liters. And T2 is 273 Kelvin, that is STP temperature at STP 273 Kelvin. T1 is 6 degrees Celsius. I am converting that 6 degrees Celsius into Kelvin. So 6 plus 273 will be 279 into P2 value. Pressure at STP will be 10 to the power of 5. So if we cancel, if we multiply this 758 with 133, you will get a value of 10 power 5. This 10 power 5 and this 10 power 5 will get cancelled. So the remaining will be 35 into 10 to the power of minus 3 into 273 divided by 279. So you will at last, if you solve this, you will get a value of 33.95 into 10 to the power of minus 3 liter. That is more or less equal to 34 ml. So the volume at final volume will be 34 ml.